In July 1940, the state of Washington opened the third longest suspension bridge on Earth. The Tacoma Narrows Bridge was celebrated as an engineering feat, defined by a sleek, minimalist steel ribbon spanning the water. Almost immediately, the design revealed an eerie quirk, and locals nicknamed the bridge Galloping Gertie. As the massive steel deck rolled in rhythmic vertical waves, the daily reality was surreal. Workers chewed gum against motion sickness, while tourists gladly paid the toll to ride the concrete roller coaster. Engineers saw the motion and scrambled to stop it. They installed heavy tie-down cables, which promptly snapped under the strain. They tried hydraulic buffers, but those failed too. Despite these glaring red flags, the bridge remained open, as the builders and the public assumed the sheer mass of all that steel and concrete made a collapse impossible. On November 7, 1940, a 42-mile-per-hour wind blew steadily across the Narrows on a brisk autumn day. Unlike the hurricane-force storms, the bridge was rated to survive. At 10 a.m. that day, the vertical bouncing transitioned into a terminal torsional twist. The deck began ringing left and right on its center axis. The human terror was immediate. A local newspaper editor, Leonard Coatsworth, had to abandon his car in the middle of the span, crawling to safety on his hands and knees as the steel groaned around him. By 11 a.m., the structure gave out, and the center span sheared away from the cables, plunging 190 feet into the icy water below. The destruction baffled the engineering world. This bridge was designed to withstand 120 miles per hour winds, yet it was destroyed by a breeze barely a third of that speed. The origins of the flaw trace back to the blueprint phase. The original plan proposed by highway engineer Clark Eldridge was a conservative design estimated to cost $11 million, relying on deep, open steel lattice trusses to stiffen the roadway. This was a proven method, plainly visible directly underneath the decks of successful structures like the Golden Gate Bridge. However, federal officials balked at the $11 million price tag. To cut costs, they brought in Leon Moyes, a star engineer of the era, who promised to deliver the crossing for only $7 million. Moyes made a crucial design change, replacing the deep open trusses with solid 8-foot-tall steel plate girders to create a much slimmer profile. That pursuit of minimalist elegance and cost reduction altered the bridge's aerodynamic profile. By swapping those open lattices for solid walls, the builder set a dangerous trap that nature would eventually spring. In a comparison of the two designs, wind passes straight through traditional open trusses, but wind crashes into the solid Tacoma girders like a sail, forcing the airflow to split. This creates turbulent vortices that alternate pulling the bridge up and down, though many falsely assumed the wind acted like a timed pendulum. Actually, as the deck tilts, wind lines bunch up against the angled surface, creating aeroelastic flutter. The trapped wind forces the flexible deck to twist further, creating a violent feedback loop of continuous alternating twists. Moysoft accidentally designed a mechanical engine perfectly calibrated to absorb energy from a steady breeze until it tore itself apart. Back on the morning of the collapse, that extreme aeroelastic flutter eventually pushed the solid steel girders past their elastic yield point. The metal bent until it could no longer snap back. The suspender cables began acting like fuses, and as they snapped one by one, they transferred impossible loads to the remaining cables in a rapid cascade until gravity won. The failure stunned the engineering community, and as the ruined center span hung mangled near the tower, Leon Moyseff's legendary career came to an end. When a replacement bridge finally opened in 1950, engineers returned to the safer open trusses and added vented slots in the roadway to ensure the wind could pass through safely. The Tacoma collapse proved that static weight calculations mean nothing without understanding fluid dynamics. Today, every major bridge on Earth requires rigorous aerodynamic wind tunnel testing before a single beam is laid. End of report.